What do I need if I'm asking for integral notation? Okay, yeah, I need that integral sign. It looks like a tall S. And then what else do I need? Okay, where do they go? What do they call them? What numbers are you talking about? Okay, what are they for this problem? Okay, where's the 0 go? On the bottom? Where's the 2 pi go? On the top? Okay, so we need to get the terminology for those two things. What are those called? Well, this one is where on the symbol? Lower. This one is where on the symbol?
It's on the
Upper.
curve.
So, and they are representing what in terms of the graph? The domain, yeah. Okay, so they are representing values on this axis here. Okay, so we call those bounds. We've got a lower bound and an upper bound. Okay, they represent the endpoints of that domain. Okay, then what do we need? The function. So we have the function itself, cosine x, and then what do we need? Dx. Okay, that differential expression. And it's just a d and then whatever variable you're looking at. Okay? So there's the integral for the cosine of x from 0 to 2 pi, which means what is that asking us to find? Okay, we'll address that question in a little bit. Okay, not necessarily derivative, because this is not a derivative notation, that's an integration notation. Okay, so let's take this, we'll stick it down here. Okay, it says, without using technology, what's the answer? So we need to know what this physically represents. Finding the integral physically represents what? Yeah, it means the area between, and Ryan says area under the curve. We have to kind of interpret the word under as trapping it between the curve and the axis. Okay, and we typically just use the term under for that. Okay, and so cosine looks like what? Where does it start? Okay, so it starts here, and then we have something that looks like this, right? That's our cosine. And so when we talk about area under the curve from 0 to 2 pi, that means we have to start trapping space between the function and the axis. And if we're going to stop it there, we have to note that we're going to chop it off there. So without using technology, in other words, I don't want you to use a Riemann sum program. I don't want you to use an fint, okay, because you have an fint like you have a deriv key if you went through the notes from yesterday. Without using technology, what is the area that we accumulate if we start at 0 and go to 2 pi? It is 0. Okay, so let me actually correct that a little bit. So that integral cosine x dx from 0 to 2 pi equals 0. Why does that value equal 0? Yeah, exactly. Amongst all the yawns and the mumbling, we've got just as much space above, which we would call what kind of area? Positive, as we do below, which we would call what kind of area, and I'm using air quotes. Yeah, negative. And so if this is positive and this is negative, this integral represents what I would call the net area, okay? It represents all our positive gains and our negative losses as we add them up. As we accumulate, and I want you to watch what I'm doing here on the board, as we accumulate going from left to right. So you can picture drawing little Riemann sum rectangles from left to right. We're going to have as many upward as we do downward. Does that make sense? Okay. Now this is where it gets a little hairy. Because if I ask you to find the definite integral, the answer is 0. Okay? But look at this next question. Knowing that the area under the function of cosine x from pi over 2 to 3 pi over 2, where is that? Where is pi over 2 to 3 pi over 2? Just this bottom part here. So this question is saying, knowing that this area, notice I'm saying knowing that this area is 2. What is the area between the function of the x-axis over the entire interval? It's a different question. We have to realize this is a different question. Exactly. What was that, Carlin? 4. Okay, when we talk about area, we're talking about actually finding the physical area. Like if I would ask you to paint that, if I would ask you to, go out on a football field and paint this for me, you wouldn't say, well, wait a minute, I'm using as much paint above the axis as I am below the axis, so I must be using 0 paint. Right? You wouldn't say that. You would say I would need 4 square yards of paint because I need to paint this entire area. So, and we ask you both questions in AP Calc. We ask you to evaluate a definite integral, but we also ask you to find the physical area. And this physical area has an area of 1 and 1 because this is split in half. So we have an area of 1 and 1, and then we also have an area of 2 underneath. So what we really have to look at when we talk about area is the absolute value of that definite integral. And so just like Carly said, the total area is 4. In other words, what I'm really looking at when I'm being asked to find the area, I'm really looking at this. Does that make sense? I'm really looking at that. That's the absolute value of integrating cosine of x. Right? We're just flipping everything positive. Okay. How are we doing so far? Is it okay? And so this is a really important distinction. If we're making this distinction between evaluating a definite integral and finding area, we're making this really important distinction of whether or not I want to accumulate a physical area or I want things to cancel out because all I'm looking for is like a net change. Okay. And so that's really the basis of section 5.3. Now, question for you. If you didn't know that the area of this piece was 2, and so that you could use some symmetry to find the total area, could you find the area without doing a Riemann sum or an F-int? Sure. Is this a geometric shape that you could do some geometry on?
Yes.
Is it a semicircle?
Yes.
No, it's not.
Yes.
Right? If it were a semicircle, we'd have undefined slope here, and the slope here, and the slope here is 1. Right? We would have something that looks like this. So these are not semicircles. Otherwise, we'd have like something like the square root of 1 plus x squared or something like that. Okay? So not semicircles. So if you didn't know that that area was 2 for this middle region, there'd be no way you could find the definite integral without using your calculator, because it's not a geometric shape. Does that make sense? In chapter 6, we'll figure out how to do that without our calculator. But for now, you would need to do an FN since it's not a geometric shape. So looking at the big picture here for chapter 5, okay, as far as evaluating definite integrals, here are the important skills so that you can do this without using technology. So as you might be kind of guessing by now, there's going to be a significant no calculator component to this chapter. Okay, being able to sketch the function for really common functions. Give me some really common functions. What functions are easy to sketch? Okay.
X.
Yeah, let's stick with lines first, right? Like f of x equals x. Or f of x equals,
No more.
yeah, or even just 4 or 4x, right? We can draw those really quickly, and we can say, hey, that's a rectangle, or hey, that's a triangle, okay? Or hey, I'm going to cut it off at 2 points to make it a trapezoid, okay? Also, semicircles. Also really common. What's the equation for a circle? X squared plus y squared equals r squared, right? Okay, let's do 1 squared, exactly. Let's have it a radius of 1. So if I solve for y, I would have something that looks like f of x equals 1 minus x squared squared root, right? We have to recognize when we see something like this that we've got a circle. And so if I ask you to integrate this, you're going to be integrating how much of a circle? Half of it, right? It's just this. Okay. Being able to find zeros for the function to see if it crosses the x-axis within the domain. That goes back, that's a lot of words, but it goes back to this. Seeing if I have positive and negative areas. And that becomes really important for finding area, because we got to change those negative areas to positive values. We can't just do an integration thing, a definite integral thing. Being able to know what the role the domain plays, and this is what Tyler was speaking to when he was saying, hey, I know the 0 and the 2 pi are my upper bound and my, whoops, let me actually write that in the other order. My lower bound and my upper bounds on my integration notation. So knowing that domain B is your start and your end points of your physical shape. Okay? And then the other important skill is, are we being asked to integrate? Or are we being asked to do some geometry? Okay? Sure can, probably. Better? Lower bound, upper bound. LB, UB. Yeah, LB, UB. So lower bound and upper bound. Okay? So those are the important skills. And those skills we're going to use in this section and the next section. Okay? How are we doing so far? All right, so the big distinction today is, am I asking you to calculate a definite integral? In which case, like for the cosine function, the answer would be 0. Or am I asking you to calculate the area between the curve and the x-axis? Or in general, we say the area under the curve. And for that first example, the answer would be 4. Same function, same domain, different answer because it turns into a geometry problem. Okay? So those are the important distinctions. So I've kind of summarized those distinctions on this third page. Okay? Definition of area under a curve. Okay? Area under a curve. Notice this gets a little confusing. They start out by saying, if, let me get my highlighter out here. If the function is not negative, in other words, if it's all above the x-axis, then my area and my definite integral are the same thing. Does that make sense? My area and my definite integral are equal. So if I have something that looks like this, the line, we'll say, just to make up stuff, f of x equals 2 plus x, right? Intercept of 2, slope of 1. Okay? If this is all positive, it's all above, so this is a positive function. Can you see then that whether I do an area or a definite integral, I get the same answer? Right? I have no negative area in my definite integral, so I have no taking away from that value. Okay? And then for any negative integratable function, not sure I said that right. Notice it's saying the area is opposite the value of the integral. So my example would be like our cosine function. I had you do that cosine from pi over 2 to 3 pi over 2. Right? If we would integrate that, we'd get an answer of negative 2. So integrating that from pi over 2 to 3 pi over 2, if you would do a Riemann sum or an F int, your answer there would be negative 2. But the area is opposite that integral. So the area is how much? Is 2. Okay. So when we're talking about positive functions, the area and the integral are one and the same. When we talk about negative functions, the area and the integral are opposites. So that last box is then what happens when we cross the axis, like our full cosine function. And there is the true definition of the integral. The integral is that positive area minus the negative area, okay? Or what I like to refer to as the net area. If we have more below the axis than above the axis, then the answer is going to be more area below than above. My answer is going to be what?
Negative.
Negative. More area above than below, then my answer is going to be positive. Okay. How are we doing so far? Okay, so we're going to use this concept. And on the next page, we've got some properties, and these properties actually have followed us throughout most of our math. Okay? And they're just basic algebraic principles. And we're kind of applying them to calculus now. So if we look at these principles, if we flip the upper and the lower bound, in other words, if I go from A to B, then I'm going from left to right. And we can think of that as like a positive delta x. But what if I go from B to A? And I work backwards. What happens to my area? Have like a negative delta x. Then my area becomes negative. So if I flip these bounds, and this becomes really helpful, all I'm going to do is flip the value of what I get for my integral. What happens if I have a function and here's A? What happens if I start my integration here and I end my integration here? How much area is underneath the curve? Nothing. Right? I started and ended at the same location, so I've got no area accumulated under the curve. Okay? For a constant multiple, if I have this constant here, I can pull the constant out. Just like working with brackets. I can factor out a constant. I can add and subtract things just like I do with the normal numbering system. And I can do that with functions. So if I have an integral of x plus cosine x from 0 to 2 pi, I can treat that as x plus cosine x. I can split it apart like that. And I can draw those two areas out then. Okay? And I can add things together. If I want to know the area, or if I want to know the integral from A to B, and then from B to C, I can literally physically add those areas. Those don't overlap at all. So if I want to go from A to B and from B to C, then I can just look at the endpoints A and C. And so we're going to use these properties to determine the area of things. Yeah. So it's an additivity. Okay. So if we look at those lower and upper bounds, I go from A to B. And then I continue from B to C, so I just keep moving all the way out to C. And that's just the same as covering from A all the way to C without stopping. Okay. So these are the properties we're gonna take a look at and have you work on at your tables. Pardon me? Did we go over the last two? Oh, 6 and 7 we're going to get into probably tomorrow.
Don't worry about it.
Yeah, don't worry about those today. I'm still digging through 6 and 7 to see how much of a factor they play in the content, in the AP content. I'm not sure they're factoring in a significant way, so I'm not sure we're going to cover them, but I got to do more digging to see if College Board emphasizes that or not. Okay, those get a little interesting as we cover those. I'm hoping that they don't stress them too much. Okay, so we know these things. If we integrate a function from 1 to 2, we get an area of -4. And if we integrate a function from 1 to 5, the same function, we get an area of +6. So this is where we're going to use these properties. And then if we integrate from 1 to 5 a different function, we get an area of 8. Do we know what the functions are? No, we don't. Do we care? Not really, because we already know what the integral is. We already know what the answer is. So let's take a look at these functions here. What if I take g of x and integrate it from 2 to 2? 0, exactly. What if I take g of x, and instead of going from 1 to 5, I go from 5 to 1?
Negative 8.
Okay, so we know those two answers. What I want you to do is I want you to work through, oh, I forgot to put boards on your desk, but I want you to work through the other 4, and then the 3 below that at your tables, and check out your answers with me. And then as you check out your answers with me, you can go ahead and move on to the web assignment.
Nope, just kidding.
But that would give you 10.
Yeah.